Hi, welcome to Solve Papers channel. I'm Godfrey. In this video, I'm solving A2 level chemistry paper 5. This is a planning, analysis and evaluation practical paper of October, November 2016. This is variant 5.2. The paper is 1 hour 15 minutes. You do not need any extra material. You only need a pen, pencil, a ruler, and your calculator for purposes of calculations, and pencil for drawing graphs. Guys, subscribe and like this video. Do you find this video useful? Please share it widely with your friends so that they may also get to benefit. Don't forget to click the bell icon so that when I upload a new video, you get an alert. Let's get started. Number 1, when hydrated barium chloride dissolves in water, barium ions and chloride ions are formed. The concentration of chloride ion in solution can be determined by titration with aqueous silver nitrate of known concentration. When silver ions react with the chloride ions, we get silver chloride, which is insoluble salt, right there. The indicator for the reaction is aqueous potassium chromate 6. At the end of the titration, it forms a red precipitate in the presence of excess silver nitrate. Silver nitrates that have not gotten the chloride ions to react with. The silver ions will react with the potassium chromate and then form a red precipitate that will indicate that the the chloride ions that were released when barium chloride dissolved in water have all been mopped up, and therefore the excess silver ion will now only react with chromate ion. That will indicate the end point. Solubilities in grams per liter of different ionic compounds at 20 degrees Celsius are given in the table below. Of course, these are cation, silver and barium. These are the anions, chloride, chromate, and sulfate. You can see barium chloride is very soluble, and silver chloride is slightly soluble. You can say it is insoluble because it dissolves very minimally. Also, barium sulfate, it is also insoluble. Barium chromate is also not that very soluble. It's also the grams per liter are very low, so it is almost insoluble. With reference to these data, where relevant, answer the following questions. The reference to this data. Right. Name the red precipitate and give an equation for the formation. The red precipitate is when silver ions react with the potassium chromate to give us silver chromate. So the red precipitate is silver chromate 6. And the equation will be silver ions in aqueous will react with the chromate ions in aqueous to give us a silver chromate 6, which is a solid. You can see silver chromate is not very soluble, so this is 2 here. So there will be a solid right there. Sulfuric acid must be added to the solution to prevent barium ions from interfering with the action of potassium chromate 6 indicator. How would barium ions interfere with the action of this indicator? The reaction of barium ions if I may come down here, when barium ions react with chromate ions, they will form an insoluble barium chromate 6 ion. Therefore, there will be no chromate ions that will be available to react with the silver to indicate to us the end point. So chromate barium ion insoluble, let me call it that, insoluble barium chromate 6 will form okay, denying the silver ions to react with the chromate ions to help indicate the end point. Right there. Part 3. How does the addition of sulfuric acid prevent barium ions from interfering with the action of this indicator? You can see barium, of course, when you add sulfuric acid, the sulfate ions from sulfuric acid will react with barium, and you can see barium sulfate will be very insoluble, so it will form a solid. So that will get the barium ions out of the way, and they will not interfere with the indicator. So these forms, when you add sulfuric acid, the sulfate ions with the barium ions forms a solid, barium sulfate, and this prevents the barium ions from reacting with the chromate. Ions. Very good. B. In an initial rough titration, excess silver nitrate solution is added so that the endpoint is exceeded. Draw a sketch graph to show how the mass of silver chloride varies with the volume of silver nitrate added. Of course, label your axis, and I will call this side here mass of precipitate. Of course, this will be in grams, and down here is the volume of silver nitrate in centimeters cubed. We are drawing a graph to show the mass of silver chloride. Silver chloride is the precipitate, so I'll call it the mass of the precipitate with the volume of silver nitrate added. So when you add the silver nitrate the mass of the precipitate will increase. So this will increase as you add the as the mass of the silver nitrate increases, then we'll have more of let me draw freehand. This is refusing. Have more of the precipitate increasing, mass of the precipitate increasing, and when all the silver nitrate has been removed, has reacted, Then addition, when all the chloride ions are being reacted, so that there are no more chloride ions, any increase of silver nitrate will not make the mass of the precipitate to increase. So the graph will look like that. The graph will look like that. I've exceeded here. Let me just bring it up to here. Very good. So that's how the graph will look like. Part C, you are to plan a titration experiment to determine the value of X in hydrated barium chloride salt. You are provided with the following materials: 3 grams of hydrated barium chloride, 0.5 moles per liter aqueous silver nitrate, 1 mole per dm cubed potassium chromate 6 solution, 1 mole per dm cubed sulfuric acid. Name 3 pieces of volumetric apparatus you would use with their capacities in centimeters cubed. You are supposed to plan a titration, so now you need the 3 pieces of volumetric apparatus. I'll go for 250 centimeters cubed graduated flask. Okay. I'll also go for 25 centimeters cubed of pipette, graduated pipette. Then lastly, I'll go for a burette. Burette is 50 centimeters cubed. Burette right there. We are doing a titration, so you need those. Part 2, describe how you would make a solution of barium chloride that is suitable for use in your titration. All right. I have 3 grams of hydrated barium chloride, so I'll dissolve the 3 grams of salt in 100 centimeters cubed of distilled water in a beaker. So dissolve the 3 grams of hydrated barium chloride. Salt provided. This is provided in 100 centimeters cubed of distilled water. We don't use tap water, use distilled water in a beaker. Then I'll transfer this into 250. Transfer the solution to 250 centimeters cubed volumetric flask. Then rinse the residue, rinse the beaker with distilled water. And add the washings to the flask. Then add more water, add more distilled water to the flask. More distilled water. To the flask to 250 centimeters cubed. Is 250 centimeter cubed of solution of barium chloride. Very good. So part 3, a known volume of barium chloride solution is transferred to a concave flask. Of course, use a burette or pipette to do that, not burette. In what order should the other 3 solutions then be added to the flask? The first one should be sulfuric acid. You need sulfuric acid there. So that sulfuric acid takes away the barium ions and frees the chloride ions. The second one is potassium chromate 6. This will be in readiness to react with excess silver. Once the silver ions have taken away all the chloride ions, the excess silver will be we'll find the chromate 6 ions available, and then they will react to give us the end point. Then now you can add your silver nitrate. Add your silver nitrate. How would you ensure that your titration results are reliable? Of course, in every titration, you're recommended to do 3 runs. Titration, repeat the titration. So titration repeated at least 3 times to get concordant results that are close to each other. Part 5. In another experiment, a student dissolves 3.13 grams of hydrated barium chloride in distilled water to give 1 liter solution. It was calculated that the concentration of barium chloride ions was 0.128 moles in every liter. Determine the value of X in hydrated barium chloride salt. Of course, here we need to calculate the mass of, we're given the concentration of barium here, which is this. Of course, we need to calculate the mass of barium chloride, so or the MR. So let's get the MR of barium chloride, and of course you're given the relative atomic masses here. So it is 137.3 plus 70. You'll get 208.3. Therefore, the mass of anhydrous barium chloride in water, so mass of anhydrous, this is without the water of hydration, this is not hydrated, so you get the mass of barium chloride in this solution of water. So mass is equals to moles times MR. So the moles are 0.0128 times the MR, 208.3. Therefore the mass will be 2.67 grams. Therefore we have this mass of barium chloride. What therefore is the mass of water in this 3.13 hydrated barium chloride? So mass of water will be equal to 3.13, take away 2.67. This will give us 0.46 grams. And we need now to get the moles of water. moles of water. You have the MR of water, the relative atomic mass or the relative molecular mass of water is 18, and now mass of water is this one, so moles of water. Moles of water is equals to mass times divided by MR, 0.46 of 18. This does give us 0.026 moles of water. Therefore, the mole ratio of barium chloride to water, the mole ratio, let me write it down here. The mole ratio is the moles of barium chloride, which is 0.0128. The moles of water is 0.026, and of course this is 2 times this, so 1 to 2. Therefore x is 2. X is 2 here. This x here is 2. D. The following information gives some hazards associated with chemicals used in the procedure. Barium chloride. Solid barium chloride is classified as toxic. Of course, it's solid chloride is a solid. So when handling, use gloves. Use gloves when handling, and of course, you need to dilute it before throw it away. Solutions equal to or more concentrated than 0.4 moles are classified as moderate hazards. Moderate hazards, and are harmful if swallowed. Solutions less than 0.4 moles per liter are classified as non-hazards. Potassium chromate 6. All solutions more concentrated than 0.9 moles per liter are classified as health hazards. And health hazards, they may cause skin, eye, and respiratory irritations, right? So in that case, you need a gas mask. You can call it nose, mouth, gas mask. Gas mask for this irritation, respiratory irritation. Of course, for skin and eyes, you need to wear gloves, and you need to have eye goggles or eye protection. Silver nitrate, solutions equal to or more than concentrated 0.18 moles per liter are classified as corrosive. They can burn, right? So solution equal to or more than 0.06 but less than 0.1 are classified as moderate hazards and cause skin, eye irritation. Solution less than this are classified as non-hazards. Very good. Identify one hazard that must be considered when planning the experiment, and describe precaution other than eye protection that should be taken to keep risks from these hazards to a minimum. So I'll go for the hazard of potassium chromate. Potassium chromate has got respiratory problems. So let's say potassium chromate 6 is hazardous is hazardous to respiratory system. Precaution is either do this experiment in a fume chamber, in fume cupboard, or you should wear nose and mouth gas mask. All right, that's the end of this question number 1. To get solved papers from 2016 to 2019, of course, go to this site, solvedpapers.co.uk. You'll get all solved chemistry paper 5 A2 from this site. The site I'm referring to is this one here. This is the site I'm talking about. It's a very resourceful site. I need you to go to chemist, to A-level chemist, Solvi 2016. Go here, and then go to A2, A-level chemist 2016. 2016 chemist A-level 2016 A2, and you click and come to this page. Not this page really. The page I'm referring to is this one here. It take you there. I'll come to this page. Chemist 2016. I'm not gone to the correct page. It is past paper, not yes, this page. 2016 November 5-2. You need this paper. That's the paper we are solving. Get this paper and then join me in working out these questions. Practice is key. Practice working out this question. You can click this green button here to get Chem Paper 5s in a soft zip folder. When you click there, you'll come here. This is paper 5 here, or these are paper 5s for 2019 all the way to 2016. Right there, November, June. So all these chemists are solved. You go to 2016. If you need this one, 2016 November, you click here. Of course, you may ask your parents to help you in acquiring these papers. They are only £10, and you'll find them very well solved and explanatory. They will help you as you revise for your chemist A2 in preparation to doing your exam in June. You may also like to know that I also do online tuitions. If you need my help, you can find me at this site, spacademy.co.uk. The site is this one here. This is the site I'm talking about here, SP Academy. Okay, this is the site I'm talking about. You can find me here. Okay, let me just go here first. You can explore the site. Maths, chemistry, biology, ICT are available. I'll need you to go to get the student guide. This will show you step by step functionalities or on how to register and get your own account with us. You might also check out this video to get familiar with the online class. Once you are done and you make up your mind you need our help, you need to register here. If you have not already done that, create your own account. We'll send you an email to activate your account. Once your account is activated, sign in, and you can click here to find a tutor. Hopefully I'll be seeing you in my tuition class. I'll be glad to help you. Number 2, sucrose is a naturally occurring sugar found in sugarcane and main fruits. It can be hydrolyzed in acidic solution to give glucose and fructose. All three molecules are chiral and will rotate the plane of polarized light. The degree of rotation is known as optical rotation, alpha. We have sucrose here. It has undergone hydrolysis in the presence of an acid to get glucose and fructose. In the presence of excess water, the reaction can be considered to be first order with respect to sucrose concentration, first order in excess water. The progress of reaction can be monitored using a polarimeter, which measures the optical rotation alpha of the solution. The more concentrated the solution, the greater the optical rotation of the solution. The more concentrated, the greater the optical rotation. The concentration of sucrose at time t can be represented as alpha minus alpha final, where alpha final is the optical rotation of the solution after 6 hours. The mathematical relationship is given by the following equation. Logarithm to base 10 of alpha minus alpha final is equals to a minus kt upon 2.30. A is a constant and k is the rate constant. K is the rate constant there. Okay. The experimentally determined values of optical rotation during hydrolysis of sucrose at 298 kelvins are recorded below. The process the results to allow you to plot a graph of this against time. Calculate this and record it to 1 decimal place. Calculate this and record to 2 decimal place. You're given the alpha final is minus 12.0. So to get this, alpha minus alpha final is equals to, for example, to calculate this we need 39.9 take away minus 12.0. This will give us 9.145. So this will be 51.9, and logarithm to base 10 of this will be 1.72. This other one here will be 29.1. Take away minus this. This will be 1.14. So 4.14. Logarithm of this to base 10 is 1.61. So you do the same for the rest, and I'll give you the values here. 3.3. 3.3. Logarithm is 1.52. For 15, this is 27.5. 144. This is 22.6. This is 1.35. This will be 18.2. Logarithm is 1.26. This will be 14.4. 14.4. Logarithm is 1.16. This will be 11.7. Logarithm is 1.07. This will be 9. We are giving this to 1 decimal point, don't forget. So this is 9.5, and logarithm here is 0.98 to 2 decimal places. The logarithm is 2 decimal places. This will be 7.5, and the logarithm will be 0.88. We have processed the results to allow you to plot a graph of this against time. So this is on the y-axis, and this is going to be on the x-axis. Time is always on the x-axis unless otherwise stated. So plot a graph on the grid on page 9 to show how this varies with time. Use a cross to plot each data point. Draw the line of best fit. Of course, after you've done that, you come here and state and explain. So shall we plot this graph? So here we are. So let's plot the graph. Time of 300. You're going to use that. So let's see the scale. This is 500 divided by 10. So each small one there is 50 seconds. On the y-axis, we have 0.6, 0.7. So difference is 0.1. Divide by 10 small squares. This will give us 0.01 on the y. This is x-axis. This is on the y-axis. So 300 will be, this is 250, this is 300 here. 300 will be, basically 300 divided by 50 will give you 6. So 1, 2, 3, 4, 5, 6 will be here, 300. 300 against 1.6. 300 against 1.61. 1.61. So 1.61 is here, 300 is here, so 1.61 is right there. Then we have 600. 600, so 600 is here. 600 is there against there's a mistake here. Let's first erase this. It was 0 is 1.72. Actually, that was also okay. 300 is there. So 0 is 1.72. 0 is 1.72. 1.72 is there. Then this one was 6 is 1.61 is there for 300. For 300 here. 600, 300 is there. 600 is right there. 600 for 1.52. 600 for 1.52. 1.52 is there. Go for 900. This is 900 is here. 900 for 1.44. 1.44. So 900 for 1.44. 1.44 is there. 1.44 is right there. Next one is 1,200. This is 1,100. 1,200 is there. 1,200 for 1.35. 1.35. So 1.35 is there. Right. 1.35 is there. 1.1500 seconds. 1500 seconds is 1.26. 1.26. 1.26. 1.26 is right there. 1800, 1600, 700, 800 is here. 1800. No, it's not. Okay. Yeah, 6, 7, 8, 9, yeah. 800 is there. It's 1.6, 1.16, 1.1 is there, 6 is there. Very good. We've 210 to 2100. 2100 is here. For 107, 107. 107 is here. Then we have 2400. 1, 2, 3, 4. 400 is there for 0.9898. It's right there. And we have 2400. We plotted. Then 2700. 6, 7. 7 is there. 7, 4.88. This is 8. This is 8, 8, 8 is here. Very good. We have plotted the graph. Plot a graph. Plot a graph and then draw the line of best fit. Draw a line of best fit. Let's zoom out on this one. Yeah, we have all the points there now. Let's draw a line of best fit. So let's start from here, going downwards. What's wrong with this? Something like that, I suppose. But this is not a good line of best fit. Don't like that. Let's try and see whether I can get a better one. Bear with me, guys, as I tried my best. Not yet. I don't know what's the issue here. All right, let's assume that is it. Although it's a little bit off on one point, I'll go with that. I'll go with that, guys. I hope you can do a better job than I have done there. All right, there it is. State, part B. State and explain whether the results and your graph confirm the relationship. This, and the answer is yes. A result is yes. The explanation, that is the stating there. The explanation is that most of the points are along the line. Most of the points, as you have seen, along the line of best fit, along the line of best fit. Very good. Part C1, determine the gradient of the graph. State the coordinates of both points you use for your calculations. Record the value of the gradient to 3SF. I'll use these coordinates here. I'll use 500 and 1.56, and your point should be as far apart as possible, and this. You pick the points on the graph. Pick the points on the graph, not the points on the table. So change in y over change in x. So gradient is equals to 1 minus 1.56 divided by 2350 minus 5. This should give you approximately 3.027027 times 10 to the power minus 4. Of course, it's going to be negative. Therefore, the gradient is -3 to 2 decimal places, or to 3SF, 3.03 per second times 10 raised to power minus 4 per second, power 4. Alright, use the gradient to calculate the value of k in the expression. Use the gradient. Of course, you can use the equation of straight line. Y is equals to mx plus c. Of course, we plotted against t against logarithm of this. So you can rearrange this equation. Let me rearrange this equation first. This equation will be logarithm to base 10 of alpha minus alpha final into brackets is equals to minus k t 2.30 plus a. So if you compare this with the equation of straight line, mx plus c, this is y, and m is k, and x is t. C is the y-intercept, which is n. So the gradient is m is equals to it's actually k over this, that is the gradient, is equals to of course the gradient is minus, so just write k over 2.30. So k is equals to gradient times 2.30, and the gradient is what we calculated here, 3.03 times 10 to the power minus 4 times 202.30, and what you get here is 6.969 times 10 to the power 4 minus 4, and this is approximately 7 times 10 raised to power minus 4 right there. So we are supposed to use the gradient value, which is negative, to calculate the value of k. Of course, this is negative and this is negative here, so the negative will cancel. So k, the value of k will be that. Part D. The graph below shows the results obtained from a second hydrolysis of sucrose reaction performed at a different temperature. Of course, we have this graph here. Okay. The point at t is equals to 1000 seconds is considered to be anomalous. This point here is anomalous. Suggest what caused this anomaly. Suggest what caused this anomaly. Of course, this could have been due to the reading for alpha taken too early. So the reading for alpha was taken too early. That could be the result of that anomaly right there. Okay. Part 2. Use the graph to determine half-life of this reaction. State the coordinates of both points you use in your calculation. Okay. Determine the half-life. So I will go back to the graph. Let's go back to the graph. Okay, this is the graph here. This is the graph. This point here, the half-life, this point here is since this is a first order reaction, then we look at 2 points and get their 2 points along the y-axis. You can choose whichever points you so wish. You can choose 30 and 15 because those are half. Then I'll read this point here. This point here is the y-axis is 400 divided by 10. The distance from here to the time from 0 to this is 400, and there are 10 small squares there, so 10. So each small square is 40 seconds. So if this is 200, 1, 2, 3, 3 times 40 will give us 120, so 320. So 320 here, 60 here. So this is 320 and 30. I'll pick this point here. This is 200. This is 100. This is 1000 against 15. So half-life is the difference between this and this. So the points that I've picked is 320 and 30 and 100, 320 and 1000. So let me come here. So the points that are coordinates that are picked is 320 and 30, and this is 1000 and 15. So the value of y should be half, right? Because it is concentration. Half-life is the time it takes for the concentration to decrease by half. So the half-life T half is 1000 minus 320. 1000 minus 320 will give me 680 seconds. So 680 seconds is the half-life right there. Part 3. For a first order reaction, the following relationship exists. Half-life is equals to that. Use this relationship and your answer to part 2 to determine K, the rate constant for this second hydrolysis reaction. If you have not been able to determine the half-life of this reaction, you may use value of T to be 500, though this is not the correct answer. So we want to determine K. So K is equals to 0.693 of half-life, which is 0.693 divided by 680. And when you do that, what is the answer? 0.693 divided by 680. You get value of K to be 0.001019. Okay, so this is the value of K, which is 0.001 to 3 decimal places per second. Right, state whether the temperature of the second reaction was higher or lower than that of the first. So the rate, to know whether the temperature is higher or not, you look at the values of K. Let's go back here. What is the value of K? Do you calculate the value of K anywhere? Let me see. We had calculated the value of K here. We had found the K and found that K is very little, 7 times 10 raised to the power 14. And for the second equation, the value of K is much higher. The value of K is, can call it 1 times 10 raised to the power 1 to 3, 10 raised to the power 3, compared to 7 times 10 raised to the power 14, the value of K that we got previously. So you can see the value of K here is much greater, and therefore the reaction is faster, because K is the rate constant. So the second equation, second reaction was at a higher temperature. Okay. The reason, you're told to explain your answer with reference to the answer you obtained in C part 2 and D part 3, this one and this one. If you have been unable to calculate the value of K in C part 2, you may use the value this, but you had calculated this value. So we say that the second value, which is this one, is much the second value of K is much larger. So that means the temperature must be higher. The higher the temperature, the more energized the particles, and therefore the faster the rate of reaction. Would the value of half-life change if the reactions were repeated with twice the initial concentration of sucrose? Give your answer. No, the value does not change. No, half-life is independent. Half-life is independent of concentration of sucrose, concentration of sucrose. Half-life remains constant. T-half is constant. Alright, so half-life will not change even though you increase the concentration of sucrose right there. So that's the end of this question paper. I hope you find it useful. Recommend it to your friends, share it with your friends. Get more of these solved papers from solvedpapers.co.uk. If you need my help, you can get in touch with me at spacademy.co.uk. Hopefully I'll be seeing you guys in my next video. Cheers.